Hi, thanks for joining me. Today I've got a fun limit problem for you. We have Qn denoting the smallest prime number that doesn't divide n, and we want to prove that the following limit exists, and then we want to compute that limit as well. And that is the limit as n goes to infinity of Qn over n. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so there are probably a few different solutions to this problem, but the way I'm going to present to you is quite nice. And in fact, if you were to make the problem any simpler by say, we're asking to prove that the limit exists, but suppose we just wanted to know what the limit was. So we're told the limit exists, but suppose we wanted to prove what the limit was, then that would be an easier problem. But we want to prove that the limit exists first. Anyway, I'm going to start with a lemma, and that is that every integer, which is at least 7, can be written as a sum of two co-prime integers, both of which are at least 2. So for any positive integer which is at least 7, I can find some positive integers a and b, both of which are at least 2, such that a plus b is that integer you gave me, and a and b are co-prime. The proof of this is just split up into different cases. So proof, and I guess one thing you might ask is why do we care about being bigger than or equal to 7? Well, that's just to ignore some very small cases. But anyway, proof, if n is odd, so let's say the integer you give me is n. If n is odd, then n is just equal to 2 plus n minus 2. Now, these guys here are certainly two positive integers, both of which are at least 2, which sum to n. And to check that they're co-prime, well, because n is odd, that means this guy here, n minus 2, is going to be odd, and this is even, hence they are going to be co-prime. Because this is 2, the only possible common factor they could share is 2, but n minus 2 is odd, so that's impossible. These two guys are certainly co-prime. Cool. What if n is even? Well, then that means that n is either equal to 4k, or n is equal to 4k plus 2 for some integer k. Well, if n is equal to 4k, then we can just write n is equal to 2k plus 1 plus 2k minus 1. Like so. Again, these are two positive integers, both of which are at least 2, which sum to give me n. And to check their co-prime, we're going to use a nice little trick. Suppose they have a common factor d, so d divides 2k plus 1 and d divides 2k minus 1. Well, then certainly d will divide their difference. So that would mean d would divide 2k plus 1 minus 2k minus 1, i.e. d would divide 2. But we're insisting that, well, we're supposing d is an integer which is at least 1, so that means d must be 2. Okay, so that means 2 divides 2k plus 1 and 2 divides 2k minus 1, but obviously that's not true because 2k plus 1 is odd, and as is 2k minus 1. So that means that these two guys here are certainly co-prime, and that deals with that case. And the case where n is equal to 4k plus 2 is pretty similar as well. We can just write n is equal to 2k plus 3 plus 2k minus 1, like so. Again, these two guys are clearly positive integers at least 2, which sum to give me n, because n is 4k plus 2 this time. And to check their co-prime, a similar thing. Suppose d is a positive integer which divides both these guys, then certainly d will divide their difference. So that means d is going to divide 2k plus 2 minus 2k minus 1, which means d divides 4. And without loss of generality, we can assume d is a prime. So that would mean that d is equal to 2. But of course, 2 doesn't divide 2k plus 3, and it also doesn't divide 2k minus 1 either. So that means certainly every positive integer, which is at least 7, can be written as the sum of two co-prime integers, both of which are at least 2. And the reason we have at least 7 here is because of these minus signs here. Sometimes these guys here might not be positive integers, but you can see that, just by going through the details, you can check that if n is at least 7, that's not the case. Anyway, we'll leave this lemma as it is proved. Let's move on to the next stage. Okay, so next we're going to prove another lemma, and we're actually going to use the lemma we just proved to help us prove this lemma. We have pk denoting the kth prime, and we want to prove that for k at least 3, the following inequality holds. Pk plus 1 plus pk plus 2 is less than or equal to p1 times p2 times so on, all the way up to pk. Now, because let's get into the proof. Because k is at least 3, this right-hand side here, p1 times p2 times pk, p1 times p2 times so on, all the way up to pk, is certainly going to be bigger than or equal to p1 times p2 times p3, but that's just equal to 2 times 3 times 5 which is 30, and 30 is certainly bigger than or equal to 7. So that means P1 times P2 times so on all the way up to Pk can be written as a sum of two co-prime integers. Let's call them A and B. So there exists A, B at least two co-prime, such that P1 times P2 times so on all the way up to Pk is equal to A plus B, like so. Now what we're going to do is let P just be some prime factor of A, so some prime number that divides A, and we're going to let Q be some prime number that divides Q. So P and Q are primes with P divides A and Q divides B, and without loss of generality, P is going to be strictly less than Q. Notice that P and Q can't be the same because then A and B would not be co-prime because they both share the common factor P. Right, so we have P is less than Q and the product of the first K primes is equal to A plus B. Well, notice that P divides A, and if it was the case that P divided this guy here, the product of the first K primes, then because of this equality here, this guy here would be a multiple of P, A would be a multiple of P, so therefore B would have to be a multiple of P, but we've just said that B can't be a multiple of P because otherwise A and B wouldn't be co-prime. So that means that P is not a factor of this guy here, but P is a prime, and this is the product of the first K primes, so that must mean that P is a prime bigger than each of the first K primes, so certainly we would have that P is bigger than or equal to P K plus 1, like so. But because we know that P is less than Q, and Q is also a prime, from this guy here, we must also have that Q is bigger than or equal to P of K plus 2, like so. But remember, P divides A and Q divides B, so certainly P must be less than or equal to A, and Q must be less than or equal to B. So all in all, we have that Pk plus 1 plus Pk plus 2 must be less than or equal to P plus Q. But that guy there, because P is less than or equal to A and Q is less than or equal to B, must be less than or equal to A plus B. And that guy there, we know, is just the product of the first K primes. And that gives us the proof for our lemma. Let me clean up the whiteboard and we'll continue. Okay, so now we can actually solve the problem and prove that the limit exists and actually compute the limit of Qn over n. The way we're going to do that is by taking an arbitrary positive integer m, which is at least 4. And then what we'll do is we'll show that for sufficiently large n, Qn over n is less than 1 over m. So by taking m as big as we want, we can make Qn over n as small as we want, and thus the limit as n goes to infinity of Qn over n must be 0. But of course, we've got to prove that. So you have m being at least 4, and we're going to choose any n, arbitrary n, and it's going to be bigger than p1 times p2 times all the way up to pm, like so. Next, because n is some number bigger than this, there is going to exist some k, which is going to be bigger than or equal to m, which from this guy here is just at least 4, such that n is between two values. It's going to be at least p1 times p2 times so on all the way up to pk, and it's going to be strictly less than p1 times p2 times all the way up to pk plus 1. Okay, so n is bigger than p1 times p2 times all the way up to pm, and if we kind of split that kind of end of the real line into these blocks, where each block is kind of the intervals of this form here, n is going to fall into exactly one of them, and we're going to choose that k here. So there exists k such that n is bigger than or equal to p1 times all the way up to pk, but it's less than kind of the next guy, p1 times p2 all the way up to pk plus 1. Anyway, first thing I'm going to do is find a bound on Qn. And now notice that Qn must be less than pk plus 1 plus 1. Why is that? Well, because if Qn was bigger than or equal to this guy here, then that would mean that every single prime less than this guy here would divide n. But then that would mean, so suppose this was the case, then that means that p1 times and p2 and all the way up to pk plus 1, all of these guys here would divide n. But then that would mean that p1 times all the way up to pk plus 1 would be less than or equal to n. Okay, just because these guys here are distinct primes. So you'd have n is at least this guy here, but that's clearly not the case from this inequality here. So we must have that Qn is bounded above by this guy here. So Qn is strictly less than pk plus 1 plus 1. But this thing here is certainly strictly less than pk plus 1, because 1 is certainly less than pk. And by the lemma we just had, this thing here is going to be less than or equal to p1 times p2 times all the way up to pk minus 1. And that's kind of why we need m at least 4, so that means k is at least 4, so k minus 1 is at least 3, so we can indeed apply the lemma. So Qn is less than or equal to this guy here, or strictly less than that guy there. But then we have that Qn over n is going to be strictly less than p1 all the way up to pk minus 1 over n. But if you look at this inequality here, if we just take the reciprocals of it, so if I just get rid of this one now, and then just look at the inverses of this, and then that, of course, flips the inequality sign, that's going to give us that 1 over n is less than or equal to this guy inverse. So this is going to be less than or equal to p1 times ... pk minus 1 divided by p1 all the way up to pk. But this is, of course, just 1 over pk, so 1 over the kth prime, and this is certainly going to be strictly less than 1 over m. I guess one way we can see that is because this thing here is going to be less than 1 over k, and that's going to be less than or equal to 1 over m. So this inequality here is because the kth prime is certainly going to be at least k, or strictly bigger than k. So that means 1 over the kth prime is going to be strictly less than 1 over k, and because k is at least m, that means 1 over k is at most 1 over m. So we get Qn over n is less than or equal to 1 over m, but remember, m was essentially some arbitrary positive integer which we're free to choose, and then we showed that for n sufficiently big, so n bigger than the product of the first m primes, we get that Qn over n is strictly less than 1 over m, and of course this guy here is positive because Qn is positive and n is positive, so that means that Qn is sandwiched between 0 and something tending to 0, so therefore the limit exists, and indeed the limit as n goes to infinity of Qn over n is equal to 0. And that solves the problem. I hope you have enjoyed this video. It involved a lot of different skills and kind of techniques to get to the solution. And as I said at the start, if all you wanted to do was compute the limit, then you might just be able to look at certain types of numbers and find the solution. But to prove that the limit exists is actually the hard thing, and that's what we've done just kind of essentially in this last step here. But of course, we needed the help of the two lemmas. Anyway, I'm going to stop waffling. I hope you have enjoyed this video, and I'll catch you in the next one. Have a great day.